Hey guys, welcome back to another video. In this video, we're going to be talking about Born-Haber cycles and how to calculate from these diagrams and how to form these to figure out different enthalpy changes. So first of all, let's try and remember what Hess's law specifically was, because Born-Haber cycle is basically a sort of elongated version of Hess law or Hess cycle, because it's literally the same concept of having the same enthalpy change regardless of whichever route you take or whichever many enthalpy changes you go through, as long as you get the same products from the same set of reactants. So what did the Hess law state? The enthalpy change in a chemical reaction is the same regardless of the route taken, as long as the final and initial conditions and states of the reactants and products are the same for each route. So what does this mean? If in both cases you're starting off with A plus B to form AB, it will have the same enthalpy change. Moreover, you should also make sure that both of these have the same state. Meaning, if you're starting off with A as gas, B as gas, and you end up with AB solid, in either case of this reaction, let's say this is reaction 1, this is one of the routes that is possible. The other could be, let's say, A gas plus B gas, then giving you, so let's say I erase this, and this is the Hess cycle for a random equation. In part 1, you're basically turning, this is the indirect route, and in part 1, this arrow, you're turning the molecule A2 and B2 into atoms, separate atoms, atom A and atom B, meaning 2 atoms of A and 2 atoms of B. So you're atomizing the molecules of A and B. This is the first step. What is the second step? You're turning it into, you're reacting both of these atoms and producing 2 moles of AB. You're producing 2 moles of AB. So bonds are being formed, and it's going to be an exothermic reaction. So you're forming 2 moles of AB. Fair enough. So this is route 1, or the indirect route, ID. What is the second possible case? It could be directly from A2 molecule and B2 molecule to AB product, which is solid. So this is the direct route. Now remember, in both of these cases, in both of these direct and indirect approaches, you're starting off with what? Gaseous A2, gaseous B2, and ending up with solid AB. So in both cases, in this case and in this case, the starting material and the ending material, or the starting reactants and the ending products, are the same. So as long as these conditions are met, you can rest assured that they're going to have the same change in enthalpy. Therefore, again, Hess law mentions that the enthalpy change in a chemical reaction is the same regardless of the route taken, as long as the final and the initial conditions and the states of the reactants and products are the same for each route. Now, how does this apply to the Born-Haber cycle. The Born-Haber cycle basically breaks down an equation into several individual steps. Meaning, let's say you're trying to react sodium and chlorine gas to form NaCl. What do? The first thing you do is atomize each of the elements. I've already talked about atomization in the previous video, and you should know it from AS level as well. What atomization basically means is it's turning the element into a gaseous atom. So in Born-Haber cycles, you're going to see that at the beginning, the sodium atom, the chlorine atom, both of those are turned into atoms. After that, what happens is the sodium in this example turns into an ion, a positive sodium ion. So basically from step 1, what are we getting? We are getting Na, sodium, gas, not solid, we are getting sodium gas, and we are getting, let's say, 1 mole of chlorine atom gas, Cl gas. Great. So we have atomized both of these and we have received sodium gas and chlorine gas as atoms. Next, we have to make sure that in the Born-Haber cycle, right after atomizing, you're doing the ionization process. Why is that the case? You know the end product that you want is NaCl, sodium chloride, where sodium has a charge of, since it's an ionic compound, sodium has a charge of +1 and chlorine has a charge of -1. Great. So you know that both of these atoms need to have a charge in the process of becoming the ionic compound. From the elements to becoming an ionic compound, there are several steps, and that is what the Born-Haber cycle is going to describe or break down into several steps of. Therefore, we've turned the elements into gas. Now what are we going to do? Turn them into ions. So do we turn the chlorine into a chloride ion first, or do we turn the sodium atom into a sodium positive ion first? What are we doing? Are we forming the cation first or the anion first? Always remember, the cation is going to be formed first, and this order is important. When you're going to be asked to draw the Born-Haber cycle, you should make sure that you're putting the change or enthalpy change of turning sodium into a sodium ion at the beginning, before turning the chlorine atom into a chloride atom. Why is that important? So you have to turn sodium Na to Na positive. Why? Because after you turn sodium atom into a sodium positive ion, you're releasing an electron. This very electron is gained by the chlorine atom. If the electron is not present at the beginning, the chlorine will not be able to gain any electron. Therefore, you need to make sure that the ionization energy or the sodium atom is first broken down into an ion. Therefore, the first step needs to be enthalpy change due to first ionization energy. Next comes the successive ionization energy. Let's say this was not sodium and it was MgCl2. In that case, you would have the second ionization energy, or Mg plus to Mg2 plus. Therefore, the successive ionization energy would be Mg plus to Mg2 plus plus 1 electron. This would be the successive ionization energy. But in this case, we do not have a successive ionization energy because sodium is going to form an ion with positive 1 charge. Great. So this only applies if you have metals with greater than positive 1 charge. Great. Next, now as I've already mentioned, you can touch the chlorine atom. You can work with the chlorine atom. Since you've already released an electron, now you can take that electron and put it along with the chlorine atom, form a bond, and it's going to become a chloride ion. So the chlorine atom plus E gives you Cl minus. Remember, all of these are gases, so don't forget to write the state symbol. All of these are going to be gases. So write the state symbols as well when drawing the Born-Haber cycle. So we have turned the chlorine atom into a chloride ion. This is the fourth step or the third step, depending on which compound you're working with. If in case it was not sodium, the metal was not sodium and it was aluminum, what would you do? You would have the third successive ionization energy or third ionization energy. Why? Because it will lose 3 electrons. It has to lose 3 electrons. Great. So depending on the compound form, your number of variables or number of steps can change. Therefore, don't just try to memorize any set of rules to apply it in a Born-Haber cycle. Great. Now, similarly, for the anion, you may have elements which can form or have a charge greater than or lower than -1. For example, sulfur. Sulfur could have a charge of -2. Oxygen could have a charge of -2. So in those cases, you may have more than one enthalpy changes for electron affinity. So for O-2, you could have O- plus one more electron turning into O-2. All of these are gas. Remember, all of these calculations are done with gaseous ions or gaseous atoms after the atomization process is done. Therefore, the first thing you need to do is atomize. Next, ionize. Then electron affinity. This order needs to be maintained. I have mentioned why the order matters. I'll repeat it. Ionization energy is not going to happen before atomization, since you need gaseous atoms for the ionization energy to be taking place, right? So similarly, for electron affinity, it's not going to take place before the ionization energy. Why? For electron affinity, you need an electron, and that electron is given off by the metal losing an electron. So it needs to ionize first, and then it can give you an electron, and then you will have the electron affinity. This is why the order matters. Alright, so in a Born-Haber cycle, once I show you the structure of a Born-Haber cycle, all of these concepts are going to be far more clear. So remember that from a Born-Haber cycle, you may be asked to find out any variable, be it lattice energy, be it enthalpy change of hydration solution, which I'm going to talk about later on, or enthalpy change of atomization, or any other variable, right? So you may be asked to find out any enthalpy change. Okay. Right, so Born-Haber cycle, as I've already mentioned, is an elongated version of a Hess cycle, where for the Born-Haber cycle, you're going to take into consideration the direction of arrows. You're going to maintain the structure of the boxes, meaning that, for example, in this Born-Haber cycle, right above the formation, you have enthalpy change of atomization, then ionization, then again atomization, and then again electron affinity. So this structure is sort of the norm for Born-Haber cycles, at least for the papers that is provided by Cambridge, or for A-level specifically. And yeah, for Born-Haber cycles, you need to consider the direction of arrows, meaning if it is upwards, it's going to be always an endothermic process. Meaning, if it's a reaction for formation, it's going to be exothermic. So the arrowhead is going to be downwards, right? Let's say it's enthalpy change of formation where enthalpy change of formation is not always exothermic. I've already mentioned this before. It can be both, because at times bonds need to be broken to form a compound, so it has both endothermic and exothermic processes. So it can be both exo and endo, but I'm just giving an example. So let's say for a formation of NaCl, it is exothermic. So the arrowhead is going to be downwards. You need to consider that and draw the Born-Haber cycle. So make sure your arrowheads are acting in the right direction. Great. So I understand that this Born-Haber cycle is a bit messy and it may be a bit difficult to understand. So I'll try and draw this in a separate place. Alright, so in this example, we're going to be drawing the Born-Haber cycle for NaCl. I've already drawn it for you to look over, but we're going to draw it from scratch again to give you a better understanding of how to structure the Born-Haber cycle. So what we're forming over here is NaCl. Great. So we know the final product. So at least let's start off with the final product. So we know the final product is going to be NaCl. What is NaCl? It's solid state. Always remember to have the state of the element, ion, or compound mentioned in the equation. Great. So we have NaCl, and from this we can say that if we want to have the value of enthalpy change of formation, which will be given in the question if you're asked to draw the entire Born-Haber cycle, a lot of the information, be it ionization energy, enthalpy change of atomization, electron affinity, and lattice energy, all of these values are going to be provided using the data booklet or in the question itself. So you need to use the data booklet to find the values, or if the question or the examiner is kind enough, they're going to give you all the values on the paper, right? So don't worry about the values, just draw the Born-Haber cycle and you will get the values either in the question or if not in the data booklet, and if not, those values are going to be asked in the questions later on. So you might have to figure out those values yourself. Alright, so if we want to form NaCl, what is the direct approach? Directly by formation, right? And it is already given that enthalpy change of formation is minus 411. So taking that into consideration, we can write. Now this is going to be a downward arrow because we know the enthalpy change is negative. Del HF is going to be minus 411. Great. Now also make sure you're adding the value half in front of Cl2, because you only need one atom of chlorine. Therefore, half times 2 is going to give you 1. And later on, we're going to see how the value of half is going to affect the enthalpy change of atomization, and how not to get confused by half or the value 2 beside the chlorine, beside the symbol. So a lot of people are going to make this mistake of multiplying atomization with 2 or with half just because there is a value of half in front of the chlorine. So I'm going to go over that. So therefore, we have already mentioned formation. Next up, where can we go with this equation or this set of elements? What can we do to these elements to get back to NaCl by an indirect approach? If you remember from the list of enthalpy changes that I've already gone over while discussing or introducing the Born-Haber cycle, there was a term called atomization. And we are going to start off with atomization. Now, there are two ways to do this. Either you atomize both, atomize Na, then atomize Cl2, and then do ionization, and then do electron affinity, or you can atomize Na, then ionize Na, then atomize Cl, and then do the electron affinity. This second approach is probably the one that is appreciated more, because it's going to keep your values in a good order, or in an accurate order. You're less likely to make mistakes while doing the calculations. So I'm going to follow the second method and first atomize the sodium atom and turn it into gas. Great. So we can say sodium atom is going to turn into sodium gas and keep the chlorine as it is, half Cl2 gas. We have not done anything to the chlorine gas. So for turning or atomizing sodium atom, the enthalpy changes 107, positive 107. Why positive? Because it's an endothermic process. So we know the atomization of sodium atom, and next we can do the ionization energy. What are we going to ionize? Sodium atom, and turn it into a sodium ion. What is the value of IE? IE1 is going to be plus 496. Why positive? Because it's an endothermic process where the electron is taken out, right? So bonds are broken. So IE1 is plus 496, and this is going to be Na plus still gas, because it's forming ionic gas, and it's going to have still the half moles of chlorine gas molecule. Great. So by now we have atomized sodium, then we have made it into an ion. Great. Next, what we can do after ionizing it, right, I forgot to write the electron. Right. So next we can work with the chlorine atom. And what are we going to do? First is we are going to atomize the chlorine molecule and turn it into a chlorine atom gas. Okay, so atomization of chlorine is going to give you a value of plus 122. 122, right? Great. So 122. and it's going to keep Na as it is, sodium ion plus 1 electron, and it's going to be Cl gas, only Cl, because you're just taking an atom of chlorine. Next up, after you've atomized it, what do you do next? You can work with electron affinity. Great. So for electron affinity, what do you know about first electron affinity? You know the process has a bit of attraction between the nucleus of the chlorine atom and the incoming electron. Since there is attraction, it's going to be an exothermic process, and it's going to release energy. Since it's an exothermic process, in which direction is the arrow going to be? Downwards, since it is exothermic. Great. So you can draw it's better to draw straight arrows rather than curved ones, so that it is much more clear, or the examiner doesn't get confused about in which direction your arrowhead is. So I would suggest you it's something like this. Yeah, it's something like this, so that the direction of the arrow is clear and they know that it's an exothermic process. All right, so we're going to turn chlorine into chloride, and the electron is going to be used up. Great. So sodium ion gas plus Cl minus gas, and this is going to be Ea1. So Ea1 value is minus 364. Great. So you have made an anion. Right. Next, you have all the values that you need to calculate the lattice energy, or the amount of energy released when the gaseous ions are reacted to form an ionic compound, 1 mole of an ionic compound. Therefore, we know what was the direct approach. The direct approach was taking the set of elements and directly forming NaCl, which is an exothermic process. What is the indirect approach, or the approach where the steps are broken down into 1, 2, 3, 4, 5, 6 steps? So what are you doing in the indirect approach? You're atomizing, you're ionizing, you're using electron affinity, and then using the value of, or the enthalpy change of, lattice energy. You know the definition of lattice energy, where it mentions it's the amount of energy released to form an ionic compound from its constituent ions in the gaseous state under standard conditions. Therefore, we can draw another arrow where it's definitely going to be downwards. Why? Because lattice energy for formation is always going to be an exothermic process, because bonds are going to be formed, and that is always true. Therefore, we can say del H lat, you don't know. And this is what you have to figure out. So the question, let's say, was structured in a way that you're giving all of these values, and you're asked to find out what the enthalpy change of lattice energy is, right? So what do? You draw the entire Born-Haber cycle and plug in the data or the values of enthalpy changes wherever required, and then you can use this in the equation to find out the enthalpy change of lattice energy. How do you do that? You know the direct approach. What is the direct approach? Enthalpy change of formation. What is the value? Minus 411. Which side do you put it on? It can be left or right, but let's say we're putting it on the left hand side and we're writing -411, and on the other side you're going to add all the values for the indirect approach. The indirect approach is going to be somewhat like this, right? You're starting off with the elements and then you're going back to the ionic compound through 1, 2, 3, 4, 5. Yeah, 5 steps. So let's start off with atomization, which is +107. Then we have turning it into an ion, which is going to be +496, 496. Then we are atomizing chlorine. And how many chlorine atoms are we forming? 1. Remember, we are forming 1 chlorine atom. It does not matter if you have this half in front of the chlorine atom or this 2 beside the chlorine gas. Does not matter. How many chlorine atoms are you forming in the Born-Haber cycle or for the product? 1 chlorine atom, and that is what matters. Because by definition, enthalpy change of atomization is talking about forming 1 mole of an atom, 1 mole of gaseous atom, So enthalpy change of atomization is only giving you the value or enthalpy change when you're forming 1 mole of a gaseous atom. So since the definition is talking about forming only 1 mole of gaseous atom, in this case you're going to take the entire value of enthalpy change of atomization. Let's say del H at is given let's say 122, and you're going to take this entire value and put it over here. You're not going to have this because that would be the case if only, you can't really take half of an atom. You have to take 1 mole of an atom. But if let's say there was, what could there be? If there was no half in front of the chlorine gas and there was just Cl2, you would be having 2Cl, right? And in that case you could multiply 122 with 2 and plug in twice the value of enthalpy change of atomization, since you're now using 2 moles of chlorine atom. But in this case we only need 1 mole of chlorine atom. So therefore we are going to use only 122. Okay, I've mentioned this or talked about the half in front of chlorine gas because a lot of people make this mistake of multiplying half with enthalpy change of atomization, but you don't do that. What you do is take the entire value of enthalpy change of atomization. Another thing, in the data booklet you will be given, let's say, a lot of bond energies. So let's say Cl2, there is a bond energy list for, let's say, Cl2, and it's given as, I guess, 242. You don't take the value 242. What you do is have this value. You're going to multiply half with this value. Why? Because the bond energy is actually giving you the amount of energy needed to form 2 chlorine atoms. Because from Cl2, what you're going to form is 2 Cl atoms. But enthalpy change of atomization only gives you 1 mole of chlorine atom, right? So since it gives you 1 mole of chlorine atom, you need to multiply half with this value, not 1 to 1, not with 121 or 122, whatever is given in the question paper. If it's not given in the question paper, you need to resort to the data booklet, and in the data booklet it will be given, let's say, 242. So in that case, what you do is multiply with half because you need 1 mole of chlorine atom. And for other elements as well, it might be a bit confusing. Let's say for nitrogen, oxygen, you need to make sure that you are getting the value of enthalpy change of atomization, where only 1 mole of gaseous atom is formed, right? So keep that in mind and calculate carefully, because a lot of people make this mistake with when to multiply with half and when to multiply with 2 to get the atomization energy. And I'm going to give or do a few examples so that you don't mess it up. Okay, so up till now we talked about atomization of chlorine. Great. Next up we have electron affinity, which is going to be exothermic, minus 364, or minus 364, and then we have del lat plus del H lat. We don't know the value of this, and we are going to bring this on one side and take this to the other and calculate for del H lat. Okay, take your calculator and calculate for this. Let's see if it matches. Alright, so I get a value of del H lat is giving me minus 772. Great, so it matches with the calculation I've done already before. So another thing, don't directly put the values or the enthalpy changes in your question paper. A lot of examiners might appreciate if you write it in this form, where you're denoting all the symbols, let's say del H of formation, del H of atomization, and in the bracket write down what you're atomizing, let's say sodium atom, i.e. you don't need to mention the atom because only the metal is going to be ionized. And then you have again the atomization, mention which atom, so chlorine. And electron affinity, you don't need to mention which one because there's only going to be one anion. And then del H lat, and it's applicable for the entire compound, so you don't need to mention anything else. So you should rather denote all the symbols so that you don't have any possible way to lose the mark, right? So after you've formed the equation, you put in the values and get the result. Great, so we have received minus 772. Alright guys, so again, there are two things I need to mention. That is, you may need to find out the starting point of the Born-Haber cycle and the ending point of the Born-Haber cycle for the ease of the calculation. So in this mess, let's try and figure out what the starting point is. I've already labeled it, but still, just for the explanation, from, let's say, the elements sodium and chlorine, you're getting two arrowheads pointing out of the box, meaning two sets of enthalpy changes are happening from this specific box or set of elements. One is enthalpy change of formation, the other is atomization. So we can say that this is the starting point, the elements. What is the ending point? For NaCl, you know, two arrows are pointing towards it, meaning at the end of the day, the end product that both of the root needs is NaCl. Therefore, NaCl is going to be your ending point or the final point. Great. So once you can figure out what the indirect root is and what the direct root is, you can form the equation and find out any specific variable in that equation or in that Hess cycle or Born-Haber cycle, right? So it's much easier if you box them out and write all of the values, all of the enthalpy changes in chronological order, meaning after atomization you have ionization energy, then again atomization energy, then again electron affinity, and the successive ionization energies and electron affinities are going to come after the initial ones. Meaning, if you have first ionization energy, right after that you also have the second ionization energy. Only then you move on to the next element, right? So try to keep all of those in sync and in order, so that while calculating you don't put in the wrong values. Great. So for calculation, sometimes certain values may need to be doubled or halved depending on the ionic compound. I've already given this example. So let's say for MgCl2, the electron affinity is going to be added twice, meaning that there are two chloride ions who needs the electron, or sorry, two chlorine atoms that needs the electron. Therefore, two electrons are going to be provided. From where is it going to come? From the magnesium ion, magnesium 2+ ion, that's going to release two electrons via the process of first ionization energy and second ionization energy. So you get two electrons, and then you have only one electron affinity, but for two chlorine atoms. So you multiply the first electron affinity with the value 2, Ea1 times 2, to get the total enthalpy change. You don't include Ea2 in this case because you're not forming Cl2 minus 2, and if you would be forming Cl minus 2, that would give you Ea2, or electron affinity, or the second electron affinity, sorry. So in this case, where you're forming two chloride ions, you only multiply the first electron affinity with 2. You don't bring in the successive electron affinities. So let's say it is, what could it be? Oxygen O-1. So in that case, you're going to have only the first electron affinity. In case of oxygen -2, or the oxide ion, you're going to have first electron affinity, and then you're going to have second electron affinity. In this case, where you're turning O-1 to oxide, you don't multiply Ea1 times 2. That would be wrong. A lot of people also make this mistake, so don't do this. You're supposed to add first electron affinity, then the second electron affinity, then the second electron affinity. So be careful and be logical. If it is two separate chloride ion, you multiply Ea1, electron affinity 1, with 2. If it is a charge of -2 or a charge of +2, you add the successive electron affinities or ionization energy. Great. So yeah, I've already showed this in the Born-Haber cycle. I've already talked about this as well. Great. So that's basically the concept of Born-Haber cycle. You break down the main step, or the formation, in this case enthalpy change of formation, into several individual steps, which is actually the process that Na and chlorine gas goes through to form NaCl. This is the direct approach, and this is the indirect approach of calculation, right? But always remember, at the end of the day, all of these steps are actually happening. Even if you write this direct equation, know that all of these steps must be happening so that you get the main compound or the main product. Alright, great. That's it for the Born-Haber cycle. I'll try and do a few examples in this playlist to clear out the concept.